Hello. Lecture 6. Another reason to fight climate change. If you didn't have enough already, ionomic dilution. What? What you talking about? Yep, we're going to learn right here why climate change is affecting the food that you eat in ways that you may not have anticipated, that you may have no understanding of. So the picture we're looking at here is Mauna Loa, the volcano that is in Hawaii, and it turns out it's sitting kind of calmly here, but there, if you look it up, there's some pretty dramatic images of it blowing the hell up with lava and stuff. Turns out there is a climate observatory sampling station up there that's been taking the partial pressure of carbon dioxide in the atmosphere for a very long time, and it's actually data from this weather monitoring station that has formed the basis of our understanding for the shift in carbon dioxide concentration and the origin of climate change. There it is. How can something so beautiful bode so ill? All right, I'm just going to start with pretty much the nastiest slide in this whole deck. This diagram on the left really is another way of looking at the carbon cycle. This is the carbon cycle that you saw before, but in a way more schematic form that probably will appeal to the plumbers out there. It sort of looks like the plumbing diagram of my house. Yeah, this is showing both the fast P cycle and the slow, fast C cycle and the slow C cycle. And this whole cycle, the point of this diagram is, I don't need you to memorize all these numbers or any of that stuff. But the point that I want to make with showing this, is that this cycle, a cycle, should be at a steady state. It needs to be at a steady state, meaning the flow in one direction in a cycle should equal the flow on the other side of a cycle. However, humans have been monkeying this up. And so in the diagram, the darker arrows, the darker pipes, so to speak, in this carbon cycle are the ones that are getting disrupted by humans. We're taking carbon out of the slow C cycle, this carbon that has been stored in the sedimentary rocks, basically the coal and other fossil fuels. And we've been taking that slow carbon and speeding it way the hell up by burning it and tossing it up into the fast carbon cycle, into the atmospheric carbon dioxide. All right. This is a problem because it's causing the other parts of this diagram to speed up to compensate for all of this carbon that we are liberating from what's called sequestration in the sediment, the sedimentary rocks and the coal and natural gas and stuff. So what data do we have to show all this? Well, they have done so people, for example, like geologists, like Bess Kaufman in the geology department here at Colby is kind of a geologist that takes ice cores and reconstructs climate models from the past because of those ice cores. One of the ways that we know about the carbon dioxide in the climate from thousands of years ago is by looking at these ice cores of ice that are deep down in glaciers that have captured carbon dioxide that was in the atmosphere from long ago. So the Taylor Dome ice core, the Law Dome ice core have shown that the carbon dioxide levels have been pretty stable over the last several thousand years. However, the ice core data of the Law Dome, which is more recent, shows that there was a huge spike, essentially coinciding with the Industrial Revolution. And then data from Mauna Loa in Hawaii continues that curve to show that, holy smokes, humans are doing something real to the atmosphere here. That carbon dioxide is jumping. So where is it coming from? Turns out, so if we look at the major North American carbon dioxide sources and carbon sinks, or places that carbon can be stored, cropland does represent a significant amount of stored carbon, as does forest land. We're actually storing carbon. We're storing carbon as trees in the forest. We're storing carbon as crops in agriculture. There are other ways that we're storing carbon. However, far outstripped by all of those, are far outstripped by the carbon we are liberating into the atmosphere via fossil fuels. And this is in the gasoline that we burn in our cars. It's in the electricity that we flip on the switch that was powered by coal or natural gas or whatever. We are dumping lots of it into the atmosphere. What the hell does this have to do with food, Dr. K? I'm getting there, trust me. So this is just some recent data from, not that recent, I guess at this point, 5 years old, but this is mean carbon dioxide levels at Mauna Loa. And you can see that the mean is in black, and then we have this seasonal variation. The carbon dioxide goes up in the winter, goes down in the summer. Down in the summer because the trees are growing in the summer and take up carbon dioxide and helps drive the number down. All right. So here it is. Here's how it affects everything. As atmospheric carbon dioxide increases, plants are like, yay, more food. They photosynthesize much more rapidly. Okay? Well, hold up. You told me a reason to fight climate change. We'll get there. So plants actually like having more carbon dioxide, or at least they photosynthesize more rapidly. And that, if you think about it, is because we are driving more carbon dioxide into that side of the carbon cycle equation that I showed you a few slides back, or in last lecture. So yeah, as carbon dioxide goes up, the rate of photosynthesis also goes up. And right now, the partial pressure of carbon dioxide, the carbon dioxide concentration in the atmosphere is where the arrow indicates, and you can see that as that partial pressure goes up, we still haven't reached a plateau. So plants can increase photosynthesis and fix more carbon, which seems good because the plants that are out there are able to more rapidly absorb that carbon dioxide in the atmosphere as the levels of carbon dioxide goes up. This happens for C3 and C4 plants. I didn't tell you what that meant, but you can basically say that that's tropical versus or arid versus temperate plants. So plants that live in these two different climates photosynthesize a little bit differently. That's all that means. All right. So in fact, the level of photosynthesis doesn't begin to level off until we get to roughly double the carbon dioxide level that is in our atmosphere. If we had double the carbon dioxide in our atmosphere, other climate change problems would be really serious problems. But doesn't seem to be phasing the plants. They're going to keep photosynthesizing. Well, not so fast. Let's see what the problems may exist with this. So it turns out that there is when the plants have all this carbon dioxide and they start photosynthesizing super rapidly, there's a shift in the ionome of the plants that are exposed to all this excess carbon dioxide. And remember what ionomics is. It's the measurement of the total elemental composition of a plant or an organism of any sort. This guy here, Irakli Laladze, I hope I said that right. He's a scientist that first noticed this by analyzing the complete ionome of various plants. And he has noticed the effect of elevated carbon dioxide on individual elements in various plants. The carbon goes way up, right? Because there is faster photosynthesis. But the relative amounts of nitrogen, phosphorus, potassium, calcium, sulfur, etc., 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 get depressed because the levels of those elements aren't magically going higher to match the carbon dioxide. So the end result is that the plants, even though they're growing more carbohydrates, they're becoming less nutritious for us because they don't have these other essential elements in them that we need to be nourished, right? We need a certain amount of nitrogen or phosphorus or potassium, and if the plants are relatively depleted of those elements, then they are less nutritious for us. The plants are essentially getting watered down by having too much carbon dioxide and photosynthesizing too rapidly. Ugh, God. So this is sadly a global phenomenon. It's a global phenomenon. If you look at the mean concentration of various nutrients across the entire ionome of all these different crops all over the world, you can see the locations that were sampled, and all of the ionomes of all of them have been depressed, have all been significantly depressed. Ooh. This level of increased CO2 actually significantly threatens human nutrition. This is not some fringe idea. This was published by a group, Myers et al., published in 2014 in Nature, where they looked at zinc, iron, protein, and phytate, which is another nutrient, in these 6 crops here: wheat, rice, field pea, soybeans, maize, and sorghum, which represents 3 different categories of photosynthetic plants, and also represents the vast majority of the human diet, vegetative diet. And you can see that there's a significant percent change in nutritive content, percent change in nutrients in these plants at elevated carbon dioxide levels relative to ambient CO2, right? So this is pretty alarming. This is pretty alarming data. Based upon this data, in 2017, another group of researchers projected the risk of protein deficiency heading forward in the next 30 years based on population projections. So the top panel is the current percentage of the population at risk of protein deficiency. Protein deficiency because that's one of the nutrients, right? Nitrogen is necessary to grow protein, and if the nitrogen is getting swamped out by the carbon in the atmosphere, protein deficiency is going to happen. So this is where we are in terms of protein deficiency right now. It's through most of the equatorial regions of the Earth, predominantly in Africa and a little bit in South America and India, Malaysia. So, yeah, some parts of Africa as high as 40 to 50% protein deficient populations, but not in the northern climes or the more developed economies. However, in panel B, we look at the percent of the population that is now going to be newly at risk of deficiency under elevated carbon dioxide. And then finally, in panel C, the millions of people estimated to be newly at risk of deficiency under the environmental concentration, the elevated concentration of carbon dioxide that's going to be in the atmosphere around 2050. So when you look at that, huge chunks of the earth, including the United States, are going to be newly at risk. So this is not mitigating any of the former parts of the world that were at risk for protein deficiency. This is new parts of the world that are going to be at risk of protein deficiency. Certainly China and India with their enormous populations, but even the United States with its population growth and the pressures of protein consumption, the United States is going to be at risk of protein deficiency. So they estimate that there will be about 2 million people newly at risk of protein deficiency in the United States in 20, 50, 30 years from now, simply because there's too much carbon dioxide in the atmosphere. And this is not taking into account the difficulties that exist due to the difficulties with agriculture that are going to exist due to other impacts from global climate change. It's a real issue. Those other effects are effects, for example, on the mean temperature of the planet. So as carbon dioxide goes up, it's a greenhouse gas, the planet's going to get warmer. They have predicted a number of nasty impacts. So the first panel in this chart is showing the change in crop yields and the increase in water stress and the incidence of heat waves in a change from 1.5 to 3 degrees centigrade globally across the planet. So the takeaway here is that the number of people projected to experience change in crop yields, heat waves, and water stress in 30 years goes up dramatically as the global mean temperature increases from 1.5 degrees centigrade to 3 degrees centigrade. So this is just, it seems like, 3 degrees, that's not that big a deal. It's like 75 instead of 73 or whatever. No, it's a huge deal. It's a huge amount. So 1 degree centigrade above pre-industrial levels is where we are at now. And so we'll hit 1.5 degrees with a near certainty by 2040. And it's possible that we can go even up as high as 4 degrees and change above pre-industrial levels by the time you folks are old, by the year 2100. I'll be long gone, I imagine. Okay. So, my God, are my lectures just nothing but doom and gloom? What a bummer. Well, I try to end on a positive note. There is some research that's being done that's trying to understand what the dynamics of this problem and how to fix it. So here is the U.S. Department of Agriculture's research center in Beltsville, where scientists are beginning to address these long-term questions. Here's one of the chief scientists, a plant physiologist, Louis Ziska, and he had the idea of studying preserved samples of wild goldenrod and found that the protein content in wild goldenrod had dropped significantly over the span of several decades, thanks to rising levels of CO2. So they had saved these samples of wild goldenrod and had been comparing them, because this was a plant that wasn't being cultivated, so it was not subject to any of the selective pressures of agriculture. It was simply samples that have been collected over the decades, over many decades, and they were able to use it as a test sample and compare it to current levels. So protein content has been going way down in our plant food supply because photosynthesis is skyrocketing. They have these little mini greenhouses. This is how they study it. And where the greenhouse is contained, they pump in carbon dioxide through these little probes you see here. And the green discs, I'm sorry, out of the green discs, and they measure the effect that it has on the plant growth. They pull out peppers. Here's the scientist sampling a pepper. She's going to look at the vitamin C level in that and see how elevated carbon dioxide is going to affect the vitamins. It turns out it does. And they have this little device where they can directly measure the photosynthesis, the actual rate of photosynthesis in the plants to take and have a better understanding of the rate of CO2 uptake and the effects on the nutritive value. So this research is just beginning to really understand the dynamics of the problem. And hopefully those scientists are going to be able to come up with some kind of a solution. But the best solution is to prevent the planet from blowing up and doing your part to take climate change seriously, because the consequences are hard to predict and certainly going to be devastating. All right. I love you all. I hope you're having a good day and enjoying these lectures. I'll see you next time. That's the unit on ionomics. We're done with that. Thanks. Bye.